My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 374. In this lecture, I will continue my discussion on dual form of support vector missions. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 373, where I discussed about dual form of support vector missions. Now just these are the slides which are from my previous lecture, that is lecture number 373. Again go back to the dual formulation. What is my dual formulation? Maximization over alpha I sigma I equal to 1 to n alpha I 1 by 2 into summation of I equal to 1 to n summation of j equal to 1 to n alpha I alpha j yi yj xi transpose xj such that alpha I is greater than or equal to 0. Alpha I is greater than 0 for support vectors, alpha I equal to 0 for non-support vectors, sigma I equal to 1 to n alpha I into yi equal to 0. Now we also said xi's only occur in the form of xi transpose xj. Just see, in the dual form what's happening? Xi is appearing in the form of dot product. Xi transpose xj means what? It is nothing but dot product between xi and xj. Xi transpose xj is nothing but dot product between xi and xj, which is equivalent to your cosine similarity. Xi transpose xj equal to xi dot xj, which is equal to cosine similarity between xi and xj if norm of xi equal to 1 and norm of xj equal to 1, isn't it? Your vectors, so your vectors are normalized. I can replace xi transpose xj with any similarity between xi and xj. Xi transpose xj can be thought of cosine similarity, isn't it? What is that cosine similarity? We know what is cosine similarity, isn't it? If I replace xi transpose xj with similarity between xi and xj, this is what made SVMs super popular, isn't it? We cannot interpret it in primal form, isn't it? What does it mean? In primal form it is not possible. This is what made support vector missions super popular. This as super popular as we don't get this interpretation only in the dual form. I can make this sense, isn't it? In dual form I can make this sense. That's why we often solve SVM problem in dual form, isn't it? If somebody gave similarity metric between xi and xj, sim of xi comma xj, I can do much with it in the primal form because I need explicit xi's and xj's in the primal form. When I go to the dual form, somebody gave me a similarity between xi and xj. I just plug the similarity in dual form, isn't it? By replacing xi transpose xj with the similarity, isn't it? That is sim of xi comma xj. Why we are able to do it? They are appearing in the form of dot product, which is not possible in the primal form. We will see why it is so. This similarity often written as, how can I write this similarity? Just see, this similarity I can write the similarity as this one. I can write k of xi comma xj, isn't it? Instead of similarity between xi and xj, so what happened here? I can write xi transpose xj by k of xi and xj. It can be written as maximization over alpha I sigma I equal to 1 to n alpha I minus 1 by 2 into sigma I equal to 1 to n, sigma j equal to 1 to n, alpha I, alpha j, yi, yj, yi, this is yi, yj. In the place of xi transpose xj, we were writing similarity between xi and xj, which can be replaced by k of xi comma xj. Here k is called, this k is called, what is this k? K is known as kernel function. K is known as kernel function, which is very similar to the similarity function. We will understand what is kernel function in a little while. Roughly I can say it is similarity between xi and xj. At the end of the day, I have to compute. What I have to compute? I must compute. Just see this one. Anyway, this is primal form. This is dual form. In the case of dual form, of course, this is C is greater than or equal to, what is that? How can I write? Just if you go back and check, what is that? C is greater than or equal to alpha, isn't it? This can be written as such that this term is C is, what is that term? C is greater than or equal to alpha I is greater than 0, isn't it? Anyway, what it says in the case of primal form, you are getting only xi, whereas in the case of dual form, you are getting xi transpose xj. This can be replaced by similarity between xi and xj, which can be replaced by with kernel k of xi comma xj, which is not possible in the primal form. Why? Because here xi occurring alone, it is not occurring with xj. That's what it says. Xi transpose xj, I am replacing with k of xi comma xj. Therefore, I can write maximization of alpha I sigma I equal to 1 to n. Just in the place of similarity of xi xj, I am writing k of xi comma xj. Here k is called kernel function, which is very similar to the similarity function. We will understand what is kernel function in a little while. Roughly I can say it is similarity between xi and xj. At the end of the day, I have to compute. What you have to compute? We have to compute f of xq. F of xq is sigma I equal to 1 to n alpha I yi xi transpose xq plus b, isn't it? This xi transpose xq, I can treat this xi transpose xq, I can write it as k of xi comma xq, isn't it? Even when you are computing f of xq, that is nothing but yq, isn't it? F of xq, when you are computing f of xq, xi transpose xq is only the dot product. Is only this is dot product, isn't it? That's what we discussed. This can be thought of k of xi comma xq. If you have a kernel function which intuitively tells about similarity between xi and xj, that's what kernel function all about. Anyway, we will discuss about it. You can think of k kernel is nothing but similarity for now. For every pair of xi comma xj, if you give me similarity value, for every pair of xi comma xj, if you give me similarity, I can calculate similarity value. I can find, I will repeat. What does it mean? For every pair of xi comma xj, if you give me similarity value, I can find my alpha i's. How can I find my alpha i's? From this one, I can find alpha i's. How can I find alpha i's? For every pair of xi comma xj, if you give me similarity value, I can find my alpha i's from 1, isn't it? Because in this formulation, I don't need xi comma xj explicitly. I don't need xi comma xj explicitly. I need only in the dot product form. That point is important. I need only in the dot product format or in the similarity format, dot product, or I can say similarity format, some similarity format. Solve this optimization problem If you solve this optimization problem, what will you get? I will get alpha is. Solve this optimization problem and get alpha is. When I get my alpha is, even at runtime and evaluation time, when somebody gives me xq and tells me to find corresponding f of xq, that is yq. This is anyway xi transpose xq is replaced by k of xi comma xq. I can always find, we can always find, isn't it? Anyway, we are getting alpha is here in from equation 1. That alpha is I can make use, so that if I get alpha is from equation 1, I can make use that alpha is. Now I can calculate yq. What is my yq? That is f of xq sigma I equal to 1 to n alpha I yi xi transpose xq, you know, isn't it? If you go from primal to dual, you have xi transpose xj, which is treated as kernel, that is known as kernelization. This trick is kernel trick. This is a brilliant idea in data science. Just time being understand, solving problem in dual form is very easy compared to solving SVM in primal form. Why? Because we are getting something like xi transpose xj, which can be replaced by similarity. That is essentially kernel k of xi comma yj. If I find alpha is from equation 1, I can always find yq from equation 2. Just go through this lecture, try to understand this. If you have any difficulty, please keep a comment. In my next lecture, I will discuss about an important technique in data science that is known as kernel trick. What is this kernel trick? We will try to understand in lecture number 375. Thank you very much.